So we talked about probability. Right now, we're talking about random variables, which are also called probability distributions. And we'll continue talking about that today. In particular, we'll be talking about a few different specific probability distributions that are discrete. And I'll touch on continuous random variables, which is basically the difference in one view between a bar graph and a sort of smooth function, such that the area of underneath the curve, or underneath, if you add up the areas of all of the blocks of a bar graph, then they have to sum up to 1. And then we're going to be getting into the highlight of this course, what we're building up to, which is linear regression, best fit lines. So I think today we should know enough shortly to start jumping into this line fitting algorithm. So I think that's what I'll do today, just so that way we start to touch on this topic. You can kind of see where things are going, and yeah, maybe next week touching on continuous random variables. We really should talk about continuous random variables. We'll get to it, but for today, we'll just be sticking to discrete random variables. And I might do a little bit of coding in Python as well. Partly this should maybe make things about probability distributions click a little bit more if you, I don't know, seeing code for it. Sometimes that makes it make a little bit more sense. But also, just as sort of a quick refresher on what Python is about. Like, how do you write Python? What's going on with Python code? Everybody in this course should have already had a Python class, so that will be very useful. There's some Python things that I might be doing that you haven't seen before. Nothing very difficult, but these are all very standard Python things. But in any case, when we get to the code portion, I'll try to talk about line by line what's going on, and I would very much appreciate questions about, if I write something, why is it that way if you don't know it? I think that there's at least one thing that I can think of that I'll be doing that I don't think you've seen before. But anything else, feel free to ask when we get to it. So that is sort of the roadmap of today's course. Okay, are there any questions about anything before we move on? If there's no questions, please type no. Thank you. All right. So, the last class, people said they sort of had a preference for maybe thinking about probability or probability distributions in terms of money, making bets, and whether you'll make money on your bets or not make money on your bets. That is a wholly consistent way to think about probability. So I'll lean into that view a little bit more. Before we were talking about counting, and this is where we need to continue for today. The main point of this is going to be focusing on two different ways of counting. That's counting the number of different outcomes when order matters and when order doesn't matter. The last time we were talking about having, for example, 4 blue balls and 1 red ball. And when order does not matter, that means that the numbers on the balls, you can just ignore them. It's really, you're just thinking about the colors. And so if you have 4 blue balls and 1 red ball, then the number of, this is called combinations, is 5, because you can put the red ball in the first position and then the blue balls in the rest, or you can put the red ball in the second position and then the blue balls everywhere else, or the red ball in the third position, and so on and so forth. So there's 5 ways altogether. But if you care about the numbers, here, the ball numbered 13 and the ball numbered 42 have switched places. When order doesn't matter, these look the same. You're just paying attention to the colors. But when order does matter, now the numbers are something that you pay attention to. And so these 2 sequences of balls are different. And the way to count the number of different ways of placing down 5 numbered balls is 120. So up here, when you don't care about the order, there's 5 different ways of putting balls. If you do care about the order, there's 120. So that's one thing to notice, is that on top, these are called combinations. And that's when you don't care about order. When you do care about order, these are called permutations. Okay, so there's a difference between these 2 words if you're talking about the number of combinations versus the number of permutations. Permutations, order matters. Combinations, it does not. Which is a little strange with the way that the English worked out for locks. You know, there's something called a combination lock, which is usually a lock that you need to put in some sequence of numbers in order to unlock it. But that's not really a combination lock, because the order matters. It should really be called a permutation lock. If it was a combination lock, it would be easier for a thief to crack and to open. But as it is, really it's a permutation lock. So don't get confused thinking about combinations work like a combination lock. That's actually just a really bad name for the lock. Okay. This symbol, a number with a exclamation point after it, that's called a factorial. And this is the basis of a permutation. And A factorial starts with that number, in this case 5 factorial, starts with the number 5, and then it's multiplied by one number less than it, 4, times 3, times 2, all the way until 1, and at 1 you stop. So writing anything in this way with an exclamation point is just a shorthand for writing a product that works like this. The first number is the number that comes before the exclamation point, and then it's a product of that many numbers, where each number decreases by 1. It turns out here, with the combinations, you can also work with this, sort of thinking about things in terms of permutations. And so that's what we're going to cover very quickly here at the beginning. Just to give you a heads up on notation, so we looked at these before. If you have 5 balls, this is written 5, choose 1. And this is read as 5, choose 1. That's the way that you read this. And what this means is that with 5 different objects, how many ways can you choose one of them? In this case, there's 5 ways that you can choose one of them. This is, you have one choice for where to put the red ball, and you have 5 different positions where you could place it, and so then this equals the number 5. Here, if you have 5 balls and 2 red ones, then this equals 20. 5 choose 2 is equal to 20. This is one way of thinking about it. This is the way that we derived this number 20 before. First, you place down the first red ball. There's 5 positions to do that. So pick whichever of the 5 positions you want. After you've made that choice, now there's 4 positions left. And so now you place down the second red ball, and in whatever spaces remain, that's where the blue balls go. So that's how we got this number 20. There's a different way of thinking about this choose function, and I will get to that in a minute. But first, I want to see if there's any questions about this, combinations versus permutations. I'm assuming this is something that you might have seen in some previous class before, but if this is the first time you're seeing this, I would like to know that too, because that will affect how quickly I go through stuff. Is there anybody who's never seen this before? If you have not seen this before, please type something to that effect. Excellent. Then from this example, talking about 5 balls, does it make sense just as far as this one example? Or are you lost somewhere here? Because if you're lost somewhere here, things might get more confusing. But if you're okay with this one example, it's okay. Not lost, but you've never seen it. Yeah. No, it makes sense. Okay, great. Then, right. Now, the reason why I should say quickly that we care about counting in this way is because it affects probabilities. If you're making a bet, then you want to count the number of ways that you can win, or maybe the number of ways you can lose, whatever, divided by the total number of outcomes that are possible. Generally, the total number of outcomes that are possible, that's kind of the easy part. But the number of ways that you can win, you should be able to count it. And that way you can come up with a probability. What's your probability of succeeding? So there was this example from last time about a baseball player. And we'll get back to this. I really like this example. It's a good one. Where there's a baseball player who is thrown 10 pitches, and somebody's making a bet that this baseball player needs to hit 7 out of the 10 balls, at least 7. Could be 8, could be 9, could be 10, but he has to hit at least 7. Here, order doesn't matter. Order doesn't matter because if he hits the first 7 balls, you win. If he hits the last 7 balls, you win. It doesn't matter which of the balls that he hits, he just needs to hit 7 of them. So this is a combination problem. And the first question was, for a player, if you can win $50 or you lose $50 here, then is this a game that's worth playing if the baseball player has a probability on any single hit of 0.6? So that means that more likely than not, on a single hit or on a single swing, that the baseball player will probably hit the ball. So it makes sense to bet that he will, in fact, hit the ball, because he probably will, 0.6 of the time. But you're asking that he hits 7 out of 10. So this one's... we said last time that this is not a game worth betting on. Because the expected number of hits is 6 with 10 swings. And so if you expect him to hit 6 times, but you're betting that he's going to hit 7 times, then this isn't a game that's worth playing. Now that might change if you change the amount of money, right? So if you're going to win or lose an equal amount of money, then it's not really a good game. You'll lose money. We can calculate how much you could expect to lose playing this. And then we could try to calculate at what point, what should your winnings be, such that now this becomes a game where you can make money off of it. But because this is, again, about... We started to formulate this at the end of last class, but then we hit this thing that I didn't introduce yet, and so we stopped it, and we're continuing it today. Again, this is a problem where order does not matter, but we want to be able to count the number of ways that this guy can hit 7 balls, or the number of ways that he can hit any number of balls, the number of ways he can hit 0 balls, 1 ball, 2 balls, 3 balls, 4 balls, and then that's all of the different ways that this game could play out. Yes, this was your example, which is a good one. Yeah. So far, is it worth playing? No, it's not. We got that far. But we can analyze it a little bit more. It's not worth playing because you'll, more likely than not, you'll lose money. But how much money will you lose? Is it going to be, I don't know, on average you'll lose $1 each time you play the game. I don't know, maybe it's just fun for you. So losing $1 on average, it's okay. Or maybe maybe you can say, well, this isn't a fair bet. Let's change the amount that I can win. So there's more that you can do with this example. But by itself, it's already very good. It has all of the pieces to get at least this far, that it's not worth playing with these numbers. All right. So very quickly, we're going to take a little sidetrack and talk about combinations. So here, one, order does not matter. Two, the number of k successes out of n trials. Okay, and it's written in this way. Again, that's read n choose k. And what this means is this. It's the number of k successes out of n trials. Here, exactly I want to say it. No. The number of ways to choose k things out of n things. That's the better way to say it. So n choose k. Here, I'll go back up to this example. We have 5 choose 1 and 5 choose 2. So 5 choose 1 is the number of ways to choose one thing out of 5. Here, the choose is where are you putting a red ball? You have 5 balls, one of them is special. So how many ways can you choose that one special ball out of 5? The second is 5 choose 2. That's when you have 2 red balls. So out of 5 balls, what are all of the different ways you can choose 2 things out of a set of 5? So that's the concrete example. Now, sticking with the, I don't know, I like small examples that you can sort of intuitively understand, but then they generalize. So you can start small, make sure that everything makes sense, and then you can just expand it and be confident that you're doing the right thing. So I'm gonna stick here with this example of 3 red balls and 2 red balls and 3 blue balls. And again, order does not matter, so I'm not going to number these. I just care about their color. All right, so this is one way of choosing 2 things out of 5. And then you have 5 slots. I'll call it a bin, B-I-N. So you have 5 bins, you have 5 balls. Each bin can hold 1 ball, and so you're just trying to count how many ways can you put the balls into bins. We already said this before. This is 5 times 4. This is 5 times 4, which is 20, because there's 5 choices for putting the first red ball, and there's, once you place it, 4 choices left of where to put the second red ball, and after that, there's no more choices left. The blue balls just go in the remaining places. Another way to think about this is that this is 5 factorial over 3 factorial. And the reason is 5 factorial is this, 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. So these cancel out, and you're left with 5 choose 4. So in general, n choose k is defined to be n factorial over k factorial n minus k factorial. Just a moment. Are we missing a 2 factorial here? Yes, that's right. Yeah, I'm sorry, we're missing a 2. This should all be divided by 2. This should be 10. Yeah. Sorry about that. Yeah, the reason why it's 10 is because order doesn't matter. If you place down the first ball, here, if this is the first red ball and this is the second red ball, then right, if we don't divide by 2, then we're double counting. Because maybe you put the first red ball here and then the second one here, or maybe you put the first red ball here and then the second one there. And then we would be overcounting. This should be 1 combination, not 2, because we don't care about, what do you call the 10? I'm not sure how to understand that. What do you call the 10 here? This is the number of ways to choose 2 balls out of 5. Or this is 5, choose 2. Yeah, sorry, let me amend this up here, because I don't want to have... divided by 2. And here, this dividing by 2 is because these are the same. So if you don't divide by 2, then you're double counting. You're counting red, red, blue, 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 but you're counting that in 2 different ways. You're counting it if you put the first ball in the first position, then the second ball in the second position, or if you put the first ball in the second position, and then the second ball in the first position. But these shouldn't look any different, because again, we don't care about the order. So that's fine. Great. Okay, good luck. All right. So, right. So you could think about it like this: 5 times 4 over 2, because of what I just described. I won't repeat it. This is another way of thinking about it that is maybe easier in some ways for certain problems. And it's also the definition of n choose k. So the reason why this is, like where is this coming from? Why is it n factorial, k factorial, n minus k factorial? Like that's a lot of factorials. Well, this n factorial, this is sort of pretending that we do care about order. And if we do care about order, here, we'll just stick with the concrete example. If each of these numbers, or if each of these balls had numbers, then there would be 5 ways to have the first ball, 4 ways for the second ball, 3 ways for the third ball. And so this would be the number of permutations of 5 balls. But as we can see here, this is one example permutation, partial permutation, because the blue balls don't have numbers, but you don't want to repeat. Here are the red balls. How many different ways, how many permutations are there of just the red balls? There's 2. You can, for any given placement of balls, if you're choosing 2 of them, then you can swap the one red ball with the other red ball. So you should divide your answer by 2. That's the n minus k part. I'm sorry, that's the k factorial part. So this k factorial is counting the number of permutations of this thing, and you need to divide by that. In this case, you can swap the red balls for each other, and so then you could be counting more than you should, so you correct it by dividing by the number of ways to swap those balls around. The n minus k factorial is concerning with the blue balls. So in how many ways could you swap the blue balls with each other? And once you've placed the red balls down, In this case, there's 3 positions that are open for the other balls, and you could swap them around with each other 3 factorial times. Okay, so that is where this thing comes from. You're thinking on the top here, this number of permutations of n balls, this k factorial, number of permutations of k balls, that's this type of example, and then this is the number of permutations for the remaining balls. Right? So the remaining ones, you have n, and then you take away k of them. And then that's that, whatever that number is, that's how many you have left that are not the k. Okay, let me pause for a moment and see if you guys have any questions about this. The concept of n choose k, or what this formula means, or anything like that. Okay, I'll take that as a no. Then let's go back up here to this game. A baseball player needs to swing 10 times, and he needs to hit a ball at least 7 out of those 10 times. We already know that this game is not worth playing because the baseball player, we expect him on average to hit 6 out of 10 balls. So trying to bet that he'll hit 7 is not going to happen given the payouts that we have. Things might change if you can win $100, then yeah, hey, maybe you can make money. You'll lose money more often, but when you win more than you lose. So maybe that can work out in your favor. Right. So I want to finish this. What is the expected payout? I forget who was who I was talking to the last class when we got here. Any chance you can unmute yourself and we can continue this?
Hello?
Oh, yes, it was Mateo. Okay, yeah, great. So this expected payout, this formula, first of all, the right-hand side of this, do you remember where this came from?
Yeah, it was multiplying the probabilities, the payouts
Mm-hmm.
by the probabilities of the number of hits the batter would get.
Very good. Yes, okay. And so the probability of 0 hits, we were able to calculate in this way. So if he doesn't, or I'll just have you explain it. Where does this 0.4 raised to the power of 10 come from?
Because the probability of him getting a hit is 0.6, so the
Mhm.
probability of him not is 0.4, and that would need to happen 10 consecutive times. So you multiply 0.4 by itself 10 times.
Excellent. Okay. And Can you explain the second one? I highlighted the choose thing in green, but hopefully now you can explain what this one means. The probability of getting one hit.
So we multiply 0.6, which is the probability of getting one hit, by 0.4 to the ninth, and we could do that because it doesn't matter the order that it happens, as long as he's getting one hit at some point.
So why do we multiply this by 10 choose 1? Could I get rid of this?
I don't think so, but
What's the difference between these two?
I'm not really sure, to be honest.
So the 0.6 times 0.4 to the ninth, that is hitting one ball and missing 9 of them.
Right.
Does it matter which of the 10 that he hits?
No.
So how many ways, if in 10 swings, how many ways could he hit the ball one time?
10 times.
10 times. And 10 choose 1 is equal to 10. That's why.
Okay.
Yeah, because it doesn't matter if you don't have this here, then you're going to be only calculating, for example, he hits the ball the first time and then he misses 9 times. But
Right.
by itself, it's just saying he hits the first swing, but we don't care about that. So the probability of him hitting the ball one time is actually bigger than if he only hits it on his first try. So that's why we have this 10 choose 1.
Okay.
Makes sense? All right. So maybe now you already see a pattern, but what would be the next one here?
So it would be negative 50 times 0.6 squared times 0.4 to the eighth times 10 choose 2.
Perfect. Okay. Can you explain each part of this?
So negative 50 is the payout for if you were to get 2 hits. Then the 0.6 squared is if you were to get 2 hits consecutively. I guess that's like the probability of it. And then the 0.4 to the eighth is if you were to not get a hit 8 times. And then the 10 choose 2 kind of takes into account that the 2 hits can occur at any point.
Exactly. Perfect. Okay. And I'm assuming that everybody else can fill in the rest here. Thank you very much.
No
Very good.
problem.
Right. So I'm not going to calculate this. I'll leave that up for you. But you have all of the pieces here. Let's see. You can use Google to do this. You could type in, minus 50 times 0.4. If you were to type this into Google, if you really cared about it, you could type in something like this. I'll make this bigger. That's too small. So you could do minus 50 times 0.4 caret 10 plus minus 50 times 0.6 times 0.4 to the 9 times, and then here you can just type 10 choose 1, and Google will give you an answer for this, and then plus the rest. I mean, it would take you, I don't know, a minute, 2 minutes to type all this out. I'm not going to bother because I don't care about the actual answer so much as the process behind it. But just to show you that it works. Let's see. I need to share my browser. Okay, people can see my browser, yes? Yes, okay, great. So just the beginning here. There you go. Now we got an answer. So you can, again, you can, the next thing is you lose $50 times 0.6 squared times 0.4 to the 8th times 10 choose 2, and you'll get an answer for that, and whatever, you just calculate it for the whole thing. So if you're so inclined, you can calculate this. You can use other, I don't know, Wolfram Alpha or whatever if you want. I'm just letting you know that Google can handle this type of calculation easily enough. Okay. Here. I see a question. It's the amount of trials with successes. 46.
That was in reference to earlier. I don't know who was talking specifically, but when you were breaking it down, I was just kind of giving it.
Yes, actually. Wait, I'm sorry. About which particular part? This.
It was we were talking about specifically, yeah, right, with the green highlight, and it would change every time.
Yes. So yeah, the amount of trials with successes.
Yeah.
So that's not just the green part, actually. It's the green part. It's this part. This is the number of successes. Yeah. Or the probability, I guess, of successes. Yeah. Mm-hmm. Probability of success. Yeah. All right. Very good. Thank you. And isn't difference is the counting? K would go up every time you have more hits. Yes. Well, good enough. Sure. In this case, the way that we're formulating this, yes, K would be going up each time. So N stays the same because he's swinging 10 times no matter what. The K here is how many hits he gets. So he could get 0 hits. In fact, I guess just for a good measure, I should mention that this, you could say 10 choose 0. 10 choose 0 happens to equal 1. Anything choose 0. How many ways can you choose 0 things? You can do it one way. You just don't choose. That's the one way you do it. So, yeah, in this formulation, the number does go up. That is kind of a nice property But n choose k, I'm just curious, equals n choose n minus k. This is true. This is a fact. Why is this true? Can anybody think about it? I'll give you a couple seconds. I promise you it's true. But can you think of a reason why this is true? Nobody. Okay, this isn't a big deal. Sometimes it's nice. Sometimes it can sort of you flip your thinking. Similar to when we were talking about the dragons and the caves and the princess and stuff like this, how thinking about what's the probability of a success can kind of be misleading if you're thinking in that term. But if you think about it as what's the probability of failure, somehow I think that will have your intuition more closely match the reality. So here on the left, this is the number of ways to choose k things out of n. On the right, this is the number of ways not to choose k things out of n. Very quickly, you could show this mathematically by saying that, well, n choose k is by definition n factorial over k factorial n minus k factorial. And n minus k would therefore be by definition n factorial over n minus k factorial over n minus k factorial. And that part just sort of gets canceled out. N minus n. Oh, sorry, that should be n minus k. And this is equal to k factorial. So you still get n factorial over n minus k factorial times k factorial. So in that way, they're the same. But the other way of thinking about it is, here with the balls, how many ways if I have 3 blue balls and 2 red balls, how many different combinations are there? Well, I could think about first placing the red balls. And after I make those choices, the blue balls have no choice. They just go where they go. But that should be the same as if I first place the blue balls and then the red balls have to go where they have to. And that these two things should be no different. So here, n choose k, this would be 5 choose 2 for the ways of placing the red balls. Here, n minus k, that's the blue balls. Right? I have 3 of them, if k is 2. So this is the number of ways of placing 3 balls. And so, yeah, it doesn't matter. You can place the red balls first, or you can place the blue balls first. You're going to get the same answer. All right. That's just a quick aside. Sometimes it's useful to know. Yeah, thinking about, I don't know, doing one thing first or the other, if some way just sort of seems more intuitive, do that one. You'll get the same answer. So this question of would K go up every time you have more hits? Yes, with the way that we're expressing it here. Because K is the number of times that he hits the ball. What's interesting, kind of, I don't know, maybe you don't think it's interesting, but you could do this. This would be the same thing. We're here, this is the number of ways that he could not hit the ball. So he hits the ball, or he misses the ball 10 times. How many ways can he miss every single time? Well, there's 10 ways. Here he misses 9 times, so 9. Here he misses 8 times, so 8. Turns out those are the same numbers. You can think about it either way. You could think about him succeeding and hitting the ball, or you could think about him failing and missing the ball. And the math is exactly the same. So, and the way that we formulated it here, K is increasing. You could think about it validly in another way where K decreases. That's the only thing I want to say. But you need to be consistent, right? Like you can't, well, I guess you could swap it. You don't necessarily need to be consistent. It's better if you're consistent. All right. Great. Okay, I think that this is good enough for what I want to say about this stuff. I'll talk a little bit after we get back about some concrete probability distributions. But now, mainly what we talked about this first hour was the idea of combinations, and really what this sort of symbol means, some properties of it, and that this is one way of counting. The permutations, I think, tend to be a little bit easier for people to think about, so I'm not spending so much time on this. But again, the reason why you should care about permutations or combinations is when you're figuring out probabilities. In particular, things like this is what's the expected amount of money that you can lose by making bets? You can calculate it. Like now you have all of the parts to be able to calculate, is a game worth playing? Games based on probability. Is the game worth playing? And how much can you expect to win or lose? You have all of the necessary equipment to work out those kinds of problems. So that being said, let's take a 10-minute break. We'll come back at like 3:15 and start talking about some concrete probability distributions. All right. Thanks, everybody. Paused. All right. Right, so I can... Right, so I'm recording now. Am I mute? People can hear me, yes? Okay. Huh. I don't know. Yeah, scroll up a little bit to see the binomial equation. Here. So the binomial distribution is the probability of getting k successes in n trials, where the p here, that is from the Bernoulli equation. So this is counting the number of successes in a repeated Bernoulli trial. The names here don't matter as much. I mean, just have, as long as you get the idea, it's fine. So Bernoulli, flipping a coin. Binomial, flipping the same coin many times. Okay? Great. All right. Then, yes. Now, to talk more about specifically the binomial distribution, but also to start getting our toes wet with programming, I want to try to program how this will look. First of all, I want to make sure, can you guys see this, this browser? Yes, okay. So this is something called a Jupyter Notebook. Jupyter spelled with a Y. This is, I installed this with something called Anaconda. Can you write that? Anaconda. So Anaconda is a Python package that's especially used for doing data science kind of stuff. So it can install Python as well as a bunch of different Python packages for making graphs, for making random numbers, for working with distributions, and Anaconda will just install all of it together, including this called Jupyter Notebook. You could install all of these things individually, but Anaconda just makes it sort of a one-step process. You can run Anaconda, or you can download it for Windows, Mac, Linux. It can be installed on any platform. So if you're working with this, then I recommend it. One of the packages is called this, Jupyter Notebook. And Jupyter Notebook, if you haven't seen it before, you can write, it's called markup language. So let's build a binomial distribution. And so first we import things to make a Bernoulli function. Distribution function that uses the Bernoulli function, and for we graph stuff. Great. So whatever. This is sort of what you can use Python Notebook for. You can write notes to yourself. You can whatever. You can also type Python things. So, for example, for I in range 10. By the way, this is a Python 3. Print I. Right, so then you can type Python stuff, it will run, and then the output is just there in the notebook. And so then you can save it. You don't need to run stuff again. I could make a note above, I don't know, the above is just showing printing and forward. Jupyter Notebook. Right, okay. So if you've never seen Jupyter Notebook before, that is my 2-minute introduction to it. It's very nice to have at your disposal for debugging, for sharing stuff with other people, and what have you. You can also use, if you're writing Python, anything you're familiar with. It doesn't really matter. If you used, what was it, PyCharm, I think is what they used in the introduction to programming class. I myself tend to use Microsoft Visual Studio Code. That's free. For some stuff, I like Jupyter Notebook. In this case, I'm using Jupyter Notebook because we're going to be graphing some stuff. And I think it'll be a good choice for this. Okay. So let me get rid of this. All right. So first, we're going to import libraries. Okay, so just to remind you, imports, these are taking in Python packages. So we're going to be writing a Python program. This Python program, you could copy all of this and put it inside of an IDE, or you could run it inside of a terminal. It will all work. But think about the things that I'm writing here as a Python program. So when you import something, this means that you have a certain, there are certain Python packages that you want your program to use. So I'm going to import something called NumPy. NumPy stands for like number Python. It allows you to make arrays, matrices, tensors, this kind of thing, and it we'll be using it. When I say as NP, that means that when I'm referring to NumPy, I can just type NP. I don't have to type NumPy. Similarly, matplotlib.pyplot, this is for making plots. But I don't want to say matplotlib.pyplot every time that I want to use it. Instead, I'll just type PLT. That's shorter. So when you see PLT, it's the same as writing this whole thing, matplotlib.pyplot. Seaborn is just for displaying graphs. All right, so these are the 3 packages that we're going to be using. Let's see. Sure, great. That. Just so you know, you can break this up into different lines, or you can just have it be in one box. It's all of this is sort of like one program, I guess. So So let's say we're going to flip a coin 1,000 times. And actually, it's not quite right. Let's see. So we're going to be flipping a coin 10 times, and we're going to be doing that 1,000 times. So we're going to flip a coin 10 times, 1,000 times. Oh, let's do it one time first. And probability of success. We'll call that P. Okay. So I'm just trying to think about the best way to write this program. All right, well, yeah, let's do it, whatever. So here I'll say Bernoulli because Bernoulli is just one single trial, all that it needs is the probability P of success, and it will return NP random. Let's see what that does. So if we do Bernoulli 0.5, okay. So instead of, right now, this will return true if the coin is heads, let's say, and it will return false otherwise. So if I run this many times, you'll see many different trues or falses. I would prefer it to return a 1 or a 0, though. So I'll say that if this is true, return 1, else return 0. Okay, so this is our Bernoulli random variable now. Okay, so the Bernoulli function, it's not equal to 1, it's not equal to 0. You'll see it equals 1 or 0 with a certain probability. Well, that's a long one of zeros, ones. Huh. Let's make sure that we actually get a 0 here. Huh. Hold on. Let's do it 20 times. Oh, print. Good. All right. So we get zeros sometimes, we get ones sometimes. That's our Bernoulli random variable. Okay, so we generate a random number. This is going to be a random number between 0 and 1. And if that number is bigger than 0.5, we return 1. Otherwise, we return 0. All right. Okay, now let's define, oh, actually. Okay. So here we have a Bernoulli random variable. This is just testing it. Let me make it 10 times to take up a little bit less room. All right. Fine. Now we need to define the binomial function. So functions are started with the word def for definition, then you give it a name. Here, I'll call this binomial. And the binomial distribution needs the number of trials and the probability of success. I'll remind you here. Let's go back here. So the Bernoulli is defined just by whatever this value p is. The binomial distribution is defined by the number p and the number n, like how many times you're going to do it. The k is going to range from 0 all the way up to n. So you actually don't need to know, in this case, what the k is. You could write a function that gives you for k equals something, what's the probability of it? But here, we're just going to have a big list. So we're going to do this thing n times, and we need to know p so that we can call the Bernoulli equation. So here, let's see. Let's see. Right. So I'm going to show you something called list compression. This is something that's in Python. I don't know if you've ever covered it or not. First, I'll do it without it, and then I'll do it with it. Just to show you what the difference is. So one way we could do this is for I in range n. Well, first we need to define a list where we're going to keep track of all the successes. And we're going to do our trial n times. And Just making it super explicit. By the way, now I know we're really shifting gears to now that I'm delving into some programming stuff. Is the pace that I'm going at okay for you guys? Intense. Like you're lost, or I lost you. Okay, great. Good to know. Let's see. Let's stay here. You don't need this. Don't need this yet. And could never learn Python or CSS or HTML or any of those. Okay. Good to know. Well, then for the coding stuff, I mean, you'll have a choice to use Python. You can also just use Excel, for example, for any of this. Are you okay at Excel? That's fine. Okay, great. Today I'm going to be focusing on Python, just because I didn't prepare any of this stuff in Excel. And actually, I don't know that... Yeah, you could do this in Excel. Myself, I'm more familiar with Python. So for the Python coding part, you can pay attention to the things that I'm doing when I'm coding if you care. But basically what I'm building up to is to just build some graphs to show you different examples of the binomial distribution. So I'm just going to display different graphs here, like that will look something like that. Oh, sorry. They'll look something like this at the bottom. And they'll be different based on the number n and the value p. So that's all that I'm really trying to do. I can draw it out by hand, but somehow when you code through it, you can just go through more examples faster. So, yeah. How about anybody else? Thank you for mentioning that. Yeah, because I don't know if I should be adding a commentary as I'm going through this, or if I should just type it all up and then just run it. For those that might be interested in working with Python for things, I thought this might be a good chance, if I give a commentary to it, to refresh people. I've heard from one student so far. How about the rest? Running it is fine. So just you prefer Excel. Okay, great. Then I won't give a commentary. I'll just go through it. All right. Oh. Oh. Okay, so this is what this function is doing. Just so you know, one thing that's cool in Python is here I'm defining a list, then I'm going through a for loop, and I'm going to be putting things inside of that list. You can actually combine all of that. I won't bother with it. This isn't a Python class. Who cares? Okay. Right. So here, the binomial, I'm just going to have it return the number of successes. Just, this is list compression, by the way. So instead of doing it this way, defining an empty list and then adding on to it each time, here, this is a list where each element in the list is going to be defined in a for loop. Whatever, it's just a way to define a list in like one line. All right. Oh. So it's going to be a list, and then yeah, I'll just do one trial, flipping the thing 10 times. Oh. There. Okay. That's strange. Sorry, this is this should be a longer list. What I want to do is I want to run the a Bernoulli thing many times. Why is that not working? Very strange. Oh, stupid. There we go. God. All right. Okay, so this is a list where each element of the list is running the binomial function, and I'm doing that some number of times. So here, if I do this Bernoulli, if I flip a coin, if I flip a fair coin 10 times, then the first time I do that, I get 4 heads. The second time I get 4 heads. The third time I get 6 heads, then 7 heads, then 6 heads. Okay, so that's all that we're doing so far. All right, now we just need to graph it. All right, that's what this is. Fine. Okay. Okay, so this is the plot package in Python. And we have a figure and axes. So now I'm going to be using that Seaborn. That's a distribution plot. cares? Okay. Oh. Do some other stuff here. Okay. So what we're seeing here is, no, I don't want to do this yet. We'll get there in a minute. Right. Okay. So this is showing two things. First of all, pay attention to the bars, not so much this curvy thing. That's something I don't want to talk about yet. But what these bars are, this is one time of flipping a fair coin 10 times. And here there were 2 times that you get a 1. Well, I'm sorry, here it's actually 4 times that you get a 1 and then 6 times that you get a 0. If you run this many times, you'll see you get different results, right? So sometimes you get heads more often than tails. Sometimes here you're also getting heads more than tails. Here you got the same number of heads and tails. So this is the Bernoulli distribution. If we look at the binomial distribution, this shows that these are the number of times. Let me also print that, I guess. Let me do that. No. Great. So here we flipped the coin 10 times, and we did that 5 times. 2 times, when we flipped the coin 10 times, we saw 4 heads. Another time, we flipped the coin 10 times, we saw 5 heads. One time we saw 7 heads. And one time we saw 9 heads. That's rare. Here. Okay? I will... Are there any questions about what you're seeing in this graph? Again, forget this smooth line. That's something else. But these numbers Again, this is flipping a fair coin 10 times. And I'm doing that 5 times. The first time I flip a coin 10 times, I see 5 heads. The second time I flip a coin 10 times, I see 3 heads. The third time I flip a coin 10 times, I see 6 heads, then 4 heads, then 5 heads. So 2 times I saw 5 heads. So that's what this bar is here. Or that's why the bar on 5 is higher. Once I saw 6 heads, once I saw 4 heads, once I saw 3 heads. Before our break, is there any questions about what you're seeing in this graph? No. Great. Then let's take a 15-minute break, and we'll come back at 4:25. Okay, now we're going. All right, thank you. And that's another reason why it's good to attend a lecture, because sometimes I don't record and we miss out on stuff. Sorry, guys. All right, very good. So with Emily, we were discussing this number, the number of times that we play the game. We will talk more about this next week when we talk about something called concentration, which is how there's a mean number here, which is 6, and how close are the other numbers to 6. Here, there's this, if you just look at the blocks here, they're fairly spread out, but yeah, 6 is high and whatever. There is a mathematical way to guess not only what the average is, but how far away from the average could you expect to be. And so this is sort of expectation on top of expectation. We'll get into that next week. For today, I just want to talk about probability distributions, the variables that define them, and we've just talked about one, the number of times you quote-unquote play a game. When you play a game many times, then most of the time you expect things to follow the expectation, in short. So that's what playing with this number is. When you make this number small, you can get very different kinds of results because variability is higher. But when you make the number big, things become very stable. There will be small changes in the heights of these bars, but for example, the 6 bar is always going to be highest, like consistently. All right, so that's what this number does. Let me pick on, how about Vincent? Do you have a mic?
Yeah.
Great. Now, let's pick a different number, this number. Probability of a success on 1 try. What number between 0 and 1 should I make this? You can pick any one you want.
0.4.
0.4. All right. So this says that the guy is going to hit the ball 0.4 of the time. Assuming we still play this game 10,000 times, how do you expect this graph to change?
It'll probably shift to the left.
All right, let's look. All right. Is that surprising?
Yeah, I guess. Oh, it kind of shifted to the left, but then there's also space in there.
Oh, yeah. Sorry. For some reason, I don't know why, the number 5 doesn't always show up there. Let's do it again. There we go. All right. So it did shift left. What's the highest number?
Like around 0.4.
Not 0.4, 4.
Oh, 4,
Yeah, this is the number of times he hits the ball out of 10 times. Why is it around 4?
Because
Right
when
now
you do
it's around 4.
like
Mhm.
because when you do it like thousands of times,
Mhm.
eventually it kind of just goes to around that number.
Yeah, why the number 4? Why doesn't it go around 8 or 0 or some other number? Why is it centered around 4?
Yeah, we put the probability at 0.4. So then when you do it out thousands of times, it's going to go around like, the number of times 4.
Sure. Okay. Great. Yeah. So if I play with this number, this one, you originally said that it will shift the graph either left or right. Is that right?
Yeah.
Yeah. So if I change this to point, I don't know, 9, what do you think will happen?
It'll probably shift over to like the 9 area.
All right. Let's see. All right. There you go. Again, I don't know why some numbers are not appearing. They're there. They're just not showing up on this graph, which is dumb. But okay, very good. So, thank you, Vincent. So this number, the number of times you play the game, controls the variability. Each time you run this code, how much would you expect to see the same looking kind of graph? The bigger this number, the less the graph will change. This number, as Vincent says, shifts the graph, either left or right. Now it's very much to the right. It's around 9. If you make this number closer to, I don't know, 0.3, now it shifts left, and it's around 3 each time. It will be 3 each time now because the number of times we're playing is so many. So this is a pretty stable graph. Great. Now we just have one more number. This one. How many tries? So how about eating? You have a mic? Okay, how about Catherine? All right. Brian. Question now.
Okay.
So there's 3 numbers that we're playing with to look at this graph. This one, the number of times you play the game, is how stable the graph is. This first number is how shifted the graph is to the left or to the right. So we have one more number left, the number of tries. I want to know what you think will happen if I add a 0 here, and now we have 100 instead of 10. How do you think the graph will change?
So there's more tries.
Right. So now the guy has 100 swings each time we play the game. Let me put this back to 0.6. We'll stick to the closer to the original thing. Hold on. Let me refresh the graph just because. All right. So this is what the graph looks like when the baseball player hits the ball 60% of the time, and he swings 10 times. And we make bets 10,000 times on the game. So if I add a number here, if I add a 0 on the number of tries, then how is the graph going to change?
Well, does the frequency go up and down? Because when you inserted the 10, it went up, I think. So like the bars.
Yeah, so the frequency, basically if you think about each of these bars as having a width of 1,
Uh-huh.
then the height is how much mass that bar has. All of this mass should equal 1, exactly the number 1. So here the 6 is like point, I don't know, it's close to 0.3. And then here we have 2 that are close to 0.25. So that's up to what? 0.3 plus 0.5, that's about 0.8. And so we would expect the remaining to be about 20% of the mass. But this is, think about it like you have a piece of clay that weighs 1 pound. And now you can put some amount of clay anywhere you want in bars. But you only have 1 pound. The whole thing adds up to 1 pound no matter where you put it.
So will it just like spread out more? Like would it just be more spread out? The chart.
Very good guess. Let's see. Oh. Sorry, I should do this. Bins. Yes, here. There you go. All right. So, is that what you mean when you say that it's more spread out?
Well, yeah, kind of like it was just be more like it'll be more, yeah, more bars because you're trying more times.
Yeah. Mhm.
Yeah.
Right.
Yeah, exactly. Yeah.
Great. So yeah, I mean you have more bars because I mean the first way we're playing the game, the guy has 10 tries, and if we give the guy 100 tries, well then he could hit the ball 60 times out of 100 or 70 times out of 100 or 1 time out of 100, or I mean there's 100 different ways that the game could play out any one time. So on the x-axis here, this is the number of times the guy hits the ball. Yeah, great. Is there anything else that you can say about this graph? Like why it looks this way?
Well, the frequency also went up. So by like, it's bigger frequencies now.
Oh,
That doesn't matter. It still ends up to 1, right?
correct. Yeah, it still sums up to 1. Actually, the frequencies have gone down.
Oh, down. Okay.
Here, yeah, the left-hand side, because now a high bar is 0.2.
Mm-hmm.
Like that's
okay.
yeah. Before that was 0.3, if you remember. Actually, let's just go ahead and look at it. So even though, yeah, on the graph, the bars look higher, the numbers that they correspond to are smaller numbers. But just to see it again here. Right. See, now this is at like 0.25 or something.
Yeah. Mm-hmm.
Where when you add this, when you make this bigger, nothing is going to be 0.25. Well, yeah. I guess this is still kind of 0.25. You'd expect, but right, yeah. So the frequency, this part on the left-hand side changes. Perfect.
Oh.
All right, thank you very much.
Yeah, no problem.
Right, so these are the 3 different numbers, and in fact, you can see this curvy line is looking more like what's called a normal distribution. We'll get into that next week. Don't worry about it today. The point is to understand for today this binomial distribution. It has a couple of properties. One is that especially when you increase the number of times you play, then the graph becomes very, very stable, and therefore you can talk about the way that the graph looks without changing it, because the graph is very stable. It's basically always going to look like this. Here, it looks a little different, but it's still the same. I mean, 60 is the big number. Higher numbers are very low, lower numbers are very low, and blah, blah, blah. So That's one property of this. And the bigger you make these numbers, I don't know how much longer that will take, then the less variability in the graph you would see. There, all right. Okay, so that's this number. This is graph stability. How many tries? This is sort of the spread. How many different values can the thing take? And then the probability of success, this shifts the graph left or right. All right, so that's why when I did this 10, when we're playing 10 times, the graph looks something like this. I mean, the 6 is the highest, and then things go down from there. So now we're seeing experimentally this thing that I just sort of drew, saying, oh, okay, yeah, it's going to be 6 most of the time. You'll notice I didn't write any numbers here because, I don't know, I just don't have them coming out of my head. But yeah, the graph should look something like that. And we see that the graph does look something like that. You know, the 6 is highest. The 7 is actually going to be a little bit higher than the 5 because the guy is a good batter. I mean, he bats better than 50%. So the probability of him doing well is actually a little bit higher than the probability of him doing not well. For any, like, the probability that he hits 9 is bigger than the probability he only hits 5. And that's because he's a good batter. So this is not exactly symmetrical. But okay, so those are the properties of binomial distribution. I hope that now, here, these things are clear to you. So we've seen now running simulations, the way that the binomial distribution matches what we expect. The expectation here is the number of trials times the probability. That is 6. If you increase this, then the number of trials, it should be 60. This, you would expect him to win 60 times, or to hit the ball 60 times most of the time. If you make this some other number, 50, then it will be like 35 or 30 something times. 0.6 times. Yeah. In any case, that is this. And then the variance, this describes how sort of fat the graph is. This can be fairly spread out looking, but actually this is a very small number. We'll get into this next week, not today. We'll focus a little bit more on this variance. Okay, I want to take a, let's take a really short break. We'll come back at 5, let's see, 5:30. 5:30. And then I'll give you the equation for fitting a line. Line fitting. All right, so let's come back at 5:30. Thanks, guys. Okay, so I want to introduce, welcome back, everybody. I want to introduce where we're going to be ending up in this class, which is line fitting, and how this relates to the things that we've been talking about before. So here I've drawn 4 points. Sorry, not so accurate, but whatever, it's hand-drawn. Of 4 points, we have a point at 1, 1. We have a point at 2, 2, a point at 3, 2, and a point at 4, 4. And I've drawn 2 lines, y equals x, and another one roughly y equals 0.8x plus 0.5. Where here, I'm using this way of representing a line, y equals mx plus b, where m is the slope and b is the y-intercept, where the line meets the y-axis. So here the slope is 1, and it meets the x-axis at 0, or the y-axis at 0. And this line has a smaller slope, 0.8, and it meets the y-axis somewhere else. Let me pick on Yue. Do you have a mic? Hello.
Hello. Can you hear me?
Yes, I can. Which of these lines do you think looks better? The green line or the blue line? Or y equals x or the other one?
I think the green line.
The green line. Okay. Why the green line?
Cause it meets 3 points.
Oh, because it touches 3 points.
Yeah.
Okay. Great. Just for a quick sanity check, how about this line? The orange line. Does that look like a good line or a bad line?
A bad line.
All right, why is it a bad line?
Because it is way so far to the point.
Because it's very far from all of the points.
Yeah.
Very good. Okay, great. Thank you.
Thank you.
So, Yue is perfectly correct in that the way that you should measure the goodness of a line is how close it is to all of the points. So here, the orange line is bad because it's really far away from everything. The green line, it actually touches 3 points. So it's perfectly correct on 3 points, but it's further away from 1 point, the point at 3, 2. The blue line doesn't actually touch any of the points, but it happens to be a little bit closer to the line 3, 2. So it can be hard to eyeball. Sometimes it's easy. This line is clearly bad, the orange line. But for these other lines, it's a little bit harder. They're not so different from each other. But you can say that the green line actually passes through 3 of the points. So maybe that makes it a good line. It turns out that the way to find the best fit line is the one that is closest to all points on average. And this, on average, is why we've been talking so much about probability, random variables, and stuff. That is a very loaded, important part of this. You want a line that's close to points, but it's not some number of points that it needs to be close to. It's all of the points. And you want it to, on average, be closer to all the points. And the way that you measure this is with something called a residual. So here, this blue line perfectly meets each of these, but this one, it's wrong by. In fact, this is length 1. Right? This point here is 3, 3. Therefore, it's away from 0.32 by 1. So that's the error of this line. So green line has error 1. The question is, what's the blue line's error? And here, the green line is missing there, it's missing there, it's missing here, and it's missing here. So the question is, is this, this, when you add them together, these they're not the number 1. These are these distances. When you add up each of these red lines together, is that smaller than 1? Is this less than the purple line? Equals 1. We don't know what these are yet. Okay? But this is the way that we judge the goodness of a line. You look at a line and you look at its distance from every single point, and then you add them together and take the average. Couldn't tell which one to watch for the specific topic. For this video, I will call it Random Variables 3. So we've talked about probability. That's these. Probability, probability, probability. Probability distributions. This whole thing, including today's talk. Probability distributions and random variables are the same thing. So I'm calling these random variables. Starting from next class, and I'm touching on that now, it will be linear regression. Well, actually, it'll be a mix. We'll do maybe 1 hour finishing stuff on probability distributions and then spending more time talking about line fitting. All right, so just because this is the end of class, I will give you the answer. This is you minimize the mean squared error. And so what this means is you want the minimum of the sum of the line minus a point. You square it. You square it because you don't care if the point is above or below the line. It's just wrong. So here the pluses and minuses don't matter. That's one way of thinking about it. Also, the square gets rid of negatives. Also, the square makes being far away from the line a bigger penalty. So if you're a distance 1 from the line, that's 1. If you're a distance 2 from the line, you're penalized by 4. If you're at a distance 5 from the line, you're penalized 25. So that's one way of thinking about this. It gets rid of negatives and it punishes lines for being far away from points. It's a heavy penalty. Okay, this is actually variance, and we'll get into this the next class, but you're minimizing the variance about the line. So this is why we've been talking about probability, random variables, averages, and variances, is because the way to find a best fit line is to find the line that has the smallest variance. So this is where we'll be going, and thank you, everybody. I hope you guys have a good weekend.